All right, let's continue with this. Get back to animations. Hello. Let's go on with the animations. So, yeah, we have two principally very different approaches. Any guess? Like, I'm sure that most of you have already used one of those. So, which approach have you used, like, within this course so far? Any guess? Yeah? Yeah, and when was that? Yes, that's absolutely right. So the logic behind keyframe is that, as you had in Pac-Man, you have a sprite sheet, and you actually have separate frames predefined in the sprite sheet, and you just like decide how much you need to keep each of them on the display, so how much time delay you have, and as in this case, then you just combine those different poses, so you just have them incrementally, like first pose, second pose, third one, fourth one, all of them have explicitly defined in the sprite sheet, as you had for the Pac-Man, different poses of like Pac-Man's mouth, and then that's it, you combine. Of course you can interpolate between them, but those ones still remain keyframes that define the whole animation and the direction of the movement. That's why it's called keyframe. So those are key ones, but it's not necessary to have all frames used in the animation explicitly defined like that, but they can be also interpolated. So the way it's implemented in OpenGL is that DBOs hold all those explicit poses, and we must ensure that the sequence of the indices for vertices and normals are identical. So each vertex with its index corresponds to another vertex in another pose. So we have this the same index vertex in this pose location, and the location in another pose, and another one. So we have exactly the same vertices and normals, but just their values change. This consistency is must to have successful keyframe animation, and we just then establish links. So if I have this particular vertex in this pose, let's take that, okay, simplify things. My hand palm is a vertex, so it doesn't change. I can't have new vertices defined or rearrange the links, the module itself. What changes from frame to frame is that if I want to animate this kind of movement, I just have this vertex defined again, but just the location and the surface normal changes, nothing else. And texture is actually the same as I mentioned in the beginning of the lecture. So here we define like original positions in the keyframe 1, then subsequent positions in keyframe 2, and then mix function is used to interpolate between them. So like we path first vertex like new position for the actually technically same vertex, and then twin factor, that is a parameter used in interpolation. You can control using this twin factor how much weight should be put on each of the frames. So if you want to have like stronger impact from one frame and then like less subtle impact from another frame in interpolation, you put it, you use it this like it's a floating point value between 0 and 1. So if it's 0, you just take first frame. If it's 1, you just take second frame. But if you put something in between, you have this interpolation effect. And texture coordinates are not involved. So we just repeat the same for normals and finally calculate the position. So pros and cons, any ideas? Keyframe, why it can be good, why it can be terrible idea.
Skeleton animation is not easier to make new animations.
Okay, yeah, that's true. Any other guess? Yeah? Yeah.
Takes up quite a bit of space.
Yeah, you have very cumbersome VBOs here. Yeah, it's simple and you can explicitly work with the sprite sheets that it's easy to see and understand what they are. But it's unsuitable for complex scenes, especially when like lots of things are changing in the scene, because you need to have these changes in every frame and it's very complex to prepare. And if you want to change the animation later, you need to revisit the sprite sheet and change the actual images in the sprite sheet. That is very time consuming and inconvenient. VBOs are very large and cumbersome to manage, and memory-wise also a pretty bad idea to use that, and you need to be very super consistent between the indices and vertices. You have like very clear management in that sense. Alternative is a skeleton animation. So some of you have already mentioned that. So could you please explain to your classmates what does it stand for? Yeah.
Well, the idea is that each joint or bone in the skeleton affects vertices that are near it at a different level. And for example, with a weight usually like between 0 and 1, and the higher the weight, the more it moves with that bone. And then multiple bones can affect multiple vertices, and then you get more like, usually it looks more natural because we're making a skeleton and organic hair. And it's usually used for organic characters more than, and also robots, I guess.
Yeah, or humans.
Yeah.
Yeah. Any more input from anyone? Yeah, that's actually absolutely true. It's skeleton animations stands on the similar concept as the scene graph. So there is a concept of hierarchy where each vertex is impacted to the bone, and we have weights put on different bones, how they impact the movement of this vertex, and finally, as in scene graph, we just like multiply all those transformation matrices to get the position of the vertex. But in contrast with the scene graphs, we first of all have these weights that in scene graphs there was like pure hierarchy, while here it's not that strict hierarchy, but it can be like different weights between different adjacent bones. And also we have concept of skinning, or like stretching the skin. For instance, in the scene graphs, if I move my elbow, the vertices that rise up leave the empty space, so kind of vacuum between the different parts of the hand, while for skeletal animation, the skin is literally kind of stretched, so those areas are interpolated and we don't have that empty space artifacts. And that is very important for quality of the animations. So here are like we define like principal bones, weights associated with them. I will show this in practice with the 3D object later at the end of the lecture. And then it's important to explicitly specify the animations. So what kind of movements and vertex displacements are associated with each of the state or action. Let's say walking or running, and it can be a loop. For example, if we have walking, we can have a loop how each vertex changes the position considering the bones and weights from them. So yeah, and actually it's nothing but the sequence of the poses. And here, yeah, the implementation is very simple. The bones are defined as uniforms to the shader, like uploaded to the shader as uniforms, and then we iterate through each vertex and then through each bones and get the weights and impact those bones have on the vertex, multiply them like the rotation matrices, and finally by the several the loop of the operations we end up with the final position. Yeah, yeah, this is almost, yeah, we end up with the final position of the vertex. So what we do is that we just consider all the matrices that are embedded in each of the bones that have impact on this vertex, and consider and multiply that by weight. So if the impact is very low, then the weight is low and the change of the position won't be that dramatic. For example, if I want to have a vertex that is located here on this part of my hand, like arm movement, the arm bone will have very dramatic impact on that, but the wrist bone has not that much, because it just changes this location of this part of the skin or this vertex just a little, so the weight of this one should be less, while the arm movement can dramatically impact the location of this part. So it's all about the same concept as in scene graphs, hierarchy, what impacts, so when the arm bone moves, which vertices move and how much. That's the general idea. Yeah, pros and cons is well, in comparison with keyframe, there is like we have more control. No, there is no need of all like keyframes to predefine. It's smoother to be used. We have more capabilities of interpolation that are simple. So we are not just limited and locked to particular keyframes, but we can have more freedom. However, if the skeleton is very complex, these hierarchies can become very complex and can be computationally extremely expensive, because if you have something like with lots of bones that have impact on each other, this all network can lead us to like very high computational power needs. And also like it's not very good, just skeleton doesn't make sense when we have like very elastic or deforming objects, for example a ball, or for example for a phenomenon like a fire, because they deform a lot, and these bones are simply not static. So the entire shape and representation of the object changes. For those kind of stuff, actually keyframe that looks very primitive could perform better. And yeah, by the end of the lecture, just to briefly summarize the 3D file formats, like STL does not support animations, OBJ as well. Well, you could somehow hard code it to load each pose separately as an OBJ file and then represent them as an animation. But OBJ itself in itself does not support animations, and that's not the smartest way to do that. So there are some formats that explicitly have animation support, like Collada, that comes from this Kronos group, like OpenGL guys, but I have not worked on this in practice myself, but generally they don't really encourage building this format. It's more just like higher level format for exchanging. There are like better formats according to literature, like Interquark Exchange, IQE, and MD5 Mesh that is used a lot in industry, and like FBX is also good, and there are like some opens like free FBX models that you could play with, and I'll show you a good example of that, and by the end there are some resources, so the video that I recommended, so watch it if you want to see all those theoretical stuff I have spoken about in practice, how they affect, let's say, the cartoons and how they are used by Disney, and keyframe and skeletal animations summarized by Kronos, and the implementation in OpenGL, so how those stuff are done in OpenGL. Let's go to the example. Where it is? Yeah, here you are. So this is a wolf model, and we just have like animation and different states or poses, like running, like states that are composed of sequence of the poses, running, walking. So it's the same 3D model. What makes the animation is just like a sequence of the poses and location of the vertices, actually, to make it simple, like creeping. So when it just stands like this, or it's idle, and here you can just like play how these movements look in, like, let's say, running in different, because timing is very important. You can control how fast those poses change, so you can just have a look how the timing impacts that. And interesting thing here is like what we have spoken about. So yeah, bones, like what are the bones for this wolf model? So it's skeleton based animation, and we have wolf skeleton, and we have this bones principal locations that impact the movement of the vertices, and the weights as well. Like, for example, let's say on the tail, these areas are more impacted by the movement of this greenish bone, while we have another bone, and the end of the tail is impacted more by this movement of this bone. And likewise, just like color coded weights. So the green one, its impact expands here, and then we have impact of other bones, and so on. And you can download those models for free to play with them. So I think this, which format is this? Oh yeah, it's FBX format. And it just shows like vertices, model size, etc. So if we make this, so you can see and observe how each of the bones actually move, how the skeleton moves, and how then the skeleton impacts the vertices that are located on the surface. Yeah, that's a general idea maybe about animations. Any questions so far? And just brief overview of the concepts. Are you going to use skeleton animation in your, I don't know, any of the assignments or exam Do you think it's something you will be comfortable with, or you prefer like keyframe from first assignments, just like sprite sheet based approach?
First.
It's simpler to understand.
Yeah, although that exact reason makes me suspect that they're going to have the exam in the skeleton.
Good idea.
Thank you. That's the only reason. I'll probably try to make one for like you're supposed to make something to prepare for the exam, you know, just to, in case. So you should probably try to make something with a skeleton in it just in case.
Yeah.
Should actually add that.
Brilliant idea.
Good proposal.
Yes.
Well, we have around like 12 minutes left, and I wanted to very briefly show you Mitsuba renderer. And if you are interested, then we could go through the details on the Q&A session, so if you think this is something you might need in the future. So Mitsuba is physically based renderer, so here the emphasis is on physical accuracy rather than artistically pleasant representation of the world. It's portable C++. It has support of Mac and Linux, but I haven't tried them myself. But on Windows platform, it's very smooth, very easy. It's portable. You don't need installation. You just like download the package. And for usability, it's very simple. Has we will see now, has GUI as well as command line interface. And it's scalable, very scalable, like you can run on your machine with your resources, or it supports parallelization over the cluster of the computers and over the network. So it's a pretty good tool, primarily used for scientific purposes. For just for instance, I will show you, let me see. Yeah, like for example, those ones are rendered in those dual screen in Mitsuba. Here, because of the limited amount of time, we have low, like few samples per pixel, and we have noises. But like still, the idea is to study how floor color impacts perceived material properties, and in this case translucency. So whether the black floor that absorbs a lot of light and does not reflect back makes materials look more or less translucent. And also we remove the caustics here. So it's used for this kind of stuff, but like if you want to just test and play and compare different rendering techniques, different materials, you want to see how they would look in your environment to get the general idea, it can be something of your interest. Or for example here, I just change material properties and see whether that how much it impacts perceived material. Like here absorption is very high because it's black and so on. So all those stuff are rendered using Mitsuba. It's very well documented. If we go back to here, there is a documentation that actually is very explicit and easy to read, and I will just like very quickly go through. So you have color appearance can be described as RGB color values or color spectra. So it's it's XML based. I forgot to mention that. So all the parameters are defined in XML file that I will show you shortly. Shapes, some like primitives are already predefined, implemented. You don't need to load them, like cube, sphere, cylinder, disk, but you can also load some like 3D object models like OBJ, PLY, the serialized version, and so on. and the different surface scattering models. So what we have gone through in OpenGL was like very simple FONG model where we had this diffuse lighting, ambient lighting, specular emission and specular reflection, so on. But here is like all different ways of light and matter interaction predefined. So how plastic materials behave, how like the electric metals, diffuse materials. So the light and matter interaction textures are supported, but I have not used it a lot. Subsurface scattering, we have just like one model for that. And you have phase functions, so this means what is the probability of when the photon is scattered to go in each direction. So isotropic is default when you have equal probability for all directions. And like you define different light sources, we have seen them already, like point light source, area light source, directional, sky, like an ambient. Also you can play with sensors, so what can be your camera or observer, and integrators are different rendering techniques that we have very briefly mentioned, like path tracing, photon mapping, bidirectional path tracing, all different ways to render and put all your parameters into the rendering pipeline and approach the rendering actually. We have like different films for like high dynamic range or low dynamic range and so on, and it supports transformation. So it's pretty powerful tool, very simple and pretty powerful. You have lots of things already done there for you. All you need is just to put your parameters for each of those stuff. And now I will show you it in practice, like in action. Oh yeah, from Mitsuba website you can download some demos. So like already predefined scenes if you want to, if you don't have anything to load or anything on your mind. So here are some examples that you can download and play with. I have already downloaded them. Here is, let's for simplicity's sake use GUI. Oh, come on. Yeah. And let's start maybe with my stuff. So this loads, actually it's better to show in XML. So here we have like what is a medium, what is absorption and scattering coefficient, so how much the light is absorbed by the media or how much it's scattered and bounced to other directions. What is the surrounding. We have some transformations, movement and scaling, like how many samples per pixel. To make it fast I just set it to 64, but it's usually like either like 4096 or higher to have little noise. And we have emitter defined, and so all you need, like when you play with this, is just to use this XML to pass your parameters. Okay, let's see how. So it has some preview based on the 3D mode. It will start rendering. So each square means each core. So in this case I have 4 core machine, and it loads that for me. And in the meantime I'll show you that maybe Dragon. So it uses this Dragon polygon file, but in this case I'm interested in XML to show you the properties. So here you are. We